Today, we're essentially taking a robot arm and putting it on the operating table. We're going to deconstruct it, piece by piece, from its mechanical skeleton all the way to the complex brain that controls its every move, to really understand how these incredible machines work. I mean, think about it. You see them everywhere, right? On a car assembly line, in an operating room, even helping people walk again as exoskeletons. They've totally woven themselves into our world. But have you ever really stopped to think about what's going on under the hood? How does a bunch of metal and wires achieve that kind of mind-blowing precision? Well, that's exactly the question we're going to answer. So, first things first, to really get into it, we need to be on the same page. What exactly are we talking about when we say robot arm? The formal engineering term is a robot manipulator. And it's actually a pretty good definition. It's a mechanical arm that moves an end effector. That's just the fancy word for the business end, the gripper, the welder, the scalpel. And it does this through the coordinated motion of its joints. And that phrase, coordinated motion, that's the secret sauce right there. And that coordination gets applied in so many different ways. I mean, just think about the difference between an arm that's lifting a car door and one that's helping a surgeon. The first one needs to be an absolute beast, incredibly strong and rigid. The other one needs unbelievable delicacy and precision. And an exoskeleton, that's got to be lightweight and totally safe to strap to a person. It really shows you how the specific job completely shapes the design. The form has to follow the function. And that brings us to the most basic choice you have to make when you're designing a robot. What kind of skeleton should it have? It turns out, just like in nature, there are really two fundamental blueprints that almost every robot arm follows. On one side, you've got your serial or open chain robots. The best way to picture this, just look at your own arm. You've got your shoulder, then your elbow, then your wrist, all one after the other in a series. This gives you a huge reach and a ton of dexterity. On the other side, you have parallel or closed chain robots. For this, think of one of those big flight simulator platforms. You've got multiple arms connecting the base to the cockpit. It can't reach very far, but because that load is shared across all those arms, it's incredibly strong and stable. And this table just lays out those engineering trade-offs perfectly. It's this classic battle in robotics. Do you want more reach or more stability? A serial arm gives you this massive workspace, but it's not as stiff at the end. A parallel arm has a way smaller workspace, but wow, is it rigid and strong for its size. So if you need to reach deep inside a machine, you go with a serial arm. If you need to hold a very heavy camera perfectly still, a parallel design is your winner, hands down. Okay, so we've got the skeleton picked out. But a skeleton is useless if it can't move, right? So let's talk about the joints. Now, most of the movement comes from two main types. You've got revolute joints, which are basically just hinges that rotate, and prismatic joints, which slide back and forth in a straight line. But this is where things start to get really, really interesting, with newer ideas like continuum joints that can bend and sneak around like an octopus tentacle, and flexible joints that have a little bit of springiness or give built right into them. And this right here is one of the biggest challenges in modern robotics. All that flexibility is incredible. It could let a robot squeeze through a tight space or gently pick up a piece of fruit, but it is an absolute nightmare to control. Trying to predict exactly how a bendy arm is going to move and vibrate is just worlds harder than calculating the motion of a simple, rigid arm. So that flexibility is both a superpower and a super headache for engineers. Which actually is the perfect segue to our next section, the brains. Because you can have the most amazing robot skeleton with the coolest joints, but without a really smart control system, it's just a very, very expensive sculpture. When you boil it all down, controlling a robot arm is kind of like a three-step dance. The first step is kinematics. That's the geometry part. It answers the question, if my joints are all at these specific angles, where exactly is my hand? The second step is dynamics. That's the physics. It answers, okay, how much force or torque do I need to apply to each joint to get the motion I want? And the final step is control. That's the execution, where the system sends thousands of precise electrical signals every second to the motors to make it all happen. But here's the catch. Those physics models, they're never 100% perfect. In the real world, there's always a little extra friction, or the metal flexes a tiny bit, or some other thing you just can't perfectly predict. And that's where AI is becoming a game changer. Engineers are using it to let the robot learn its own quirks and unique dynamics through trial and error. This helps it correct for those tiny errors in the model, and it can even learn to predict when one of its own parts might be about to break. And the results? They're pretty staggering. This quote is from a study where they used a more advanced model that took that joint flexibility into account. And look at that, position errors dropped by over 65%. To put that in perspective, that's the difference between a robot placing a microchip perfectly on a circuit board or missing it entirely. It's a massive jump in real-world accuracy. All right, so let's tie all this theory together. We've talked about skeletons, joints, and brains. Now let's look at a couple of amazing real-world examples where these design choices come to life. Okay, so you're looking at a number on the screen, -7.79%. What on earth could that mean? Well, that number represents a real measured benefit that a person got from wearing a very cleverly designed robot. Let's take a closer look. That number comes from a study on a wearable exoskeleton designed to help people carry heavy loads. It's the average reduction in the user's metabolic rate. In other words, the robot literally made their job almost 8% easier. And the way they did it was so smart. Instead of using 4 motors for 4 joints, they used a time-sharing system where just 2 motors could power all 4. This brilliant trick cut down on weight, which makes a huge difference in how tired the person wearing it gets. Now let's switch from brawn to incredible precision, the steady hand of a surgical robot. During minimally invasive surgery, you need the tools to pivot perfectly at that tiny little incision point without wiggling around and damaging tissue. To guarantee this, the robots are physically built with something called a remote center of motion constraint. The mechanics of the arm itself force the tool to pivot around that fixed point out in space. It's not just code, it's a beautiful, elegant mechanical solution that makes surgery dramatically safer. So if there's one core idea to take away from all this, it's this. There is no such thing as a perfect robot arm. There's only the perfect arm for a specific job. Every single one you see, whether it's on a factory floor or in an operating room, is a masterclass in engineering trade-offs. It's a delicate balance of reach versus stability, flexibility versus control, power versus weight, all custom-tailored to the task at hand. And that really leaves us with a pretty cool question to think about. We've seen how the tasks of today have shaped the robots of today. So what about tomorrow? What future job, maybe exploring a new planet or building things on a microscopic scale, is going to require a completely new kind of robot arm that we haven't even imagined yet? It's an exciting thing to think about. Thanks for diving in with me on this one.